When we talk about natural logs, we say that the natural log of x is log to the base e of x. So what is this e? E is Euler constant, and where does this number come from? Why is it so special? Well, this number, if we look at a graph of f of x equals b to the x, and especially say we take an example where y equals 2 to the power x. If we differentiate this from first principles, we get y plus delta y equals 2x delta x, 2x plus delta x. Okay, and differentiating from first principles, we get delta y over delta x equals 2x plus delta x minus 2 to the power x all over delta x. This, as we go take delta x goes to 0, we have delta y over delta x becomes 2x as the limit delta x tends to 0 to delta x minus 1 over delta x. So how do we then solve for this? There's no easy way to do it. What we can do is, because delta x is tending to go towards 0, choose a very small number and put that into the equation. So if we put 0.01 into the equation, we get an output of 0.693, where b is 2. Now if we choose b when b is 3, we'll get, putting the same small value for delta x, we'll get a value of 1.09. Now what this shows is that there's some value between 2, which is this here, and 3, which is 1.09, where the actual gradient or the rate of change is 1, and that actually occurs when b equals 2.71828, and that is Euler's constant. Is actually e equals a limit as n tends to infinity of 1 plus 1 over n to the power n. So if we do a quick chart of this, where we have n and we have 1 plus 1 over n to the power n. You can see that for 1 this becomes 2. At 10, we put 10 in for n, we get around about 2.5937. If we put a very large number, say going turn towards 1,000, we get 2.7048, and as it tends to infinity, e tends to go towards 2.718. Natural logarithms, the laws of logarithms also apply to natural logarithms. So the natural log of x, y equals the natural log of x plus natural log of y. Similarly, the natural log of quotient x over y equals the natural log of x minus the natural log of y. The natural log of x to a power, say b, equals b natural log x, and the natural log of e is 1. If we consider the natural log of e and standard logs, this is really log e to the base e. So we're saying e to what power gives e. E to what power gives e, and the answer is 1. So wherever we have the log e and an e next to each other, they cancel each other out, so we're left with 1. Similarly, if we have a natural log ln e, that equals 1. So natural log of e equals 1. If we have e to minus 3 natural log 4, this equals e natural log 4. By the rules of logarithm, we could move the minus 3 up, minus 3. Now we've got this natural log and this e next to each other, that equals 1, cancels each other out. So this becomes 4 to the minus 3, which equals 1 over 4 to the power 3, equals 1 over 64. Another example, say we had the natural log of x plus 2 squared equals 2. We can move the 2 down by laws of logarithms. So we have 2 natural log x plus 2 equals 2. So we have the natural log of x plus 2 equals 2 divided by 2 is 1, and then we can just write this as e to the x plus 2 equals 1, x equals e minus 2. We exponentialize the equation, so from here, if we have a little thought bubble, we did e exponentialize natural log x plus 2 equals e to the 1. Then, because this e and this natural log, like we spoke before, are next to each other, they cancel each other out and make essentially 1. So x plus 2 equals e to the 1. E to the 1, or anything to the power of 1, is itself, so that's e. So x plus 2 equals e, and then x equals e minus 2. If we had e to the x equals 6.2, we take the natural logs on both sides. Natural log of e to the x equals the natural log of 6.2. Bring the x down, so that's x. Natural log of e equals the natural log of 6.2, and then bring the natural log of e to the other side, and that becomes the natural log 6.2, and the natural log of e is essentially 1. So x equals the natural log 6.2. And this second example, e to the 2x plus 1 equals 75. So again, take natural logs both sides. Natural log of e 2x plus 1 equals the natural log of 75. Bring the 2x plus 1 down here, which we can do with the laws of logarithms. So 2x plus 1, natural log of e, is the natural log of 75. So 2x plus 1 equals the natural log of 75 over the natural log of e, which we said was 1. So 2x equals the natural log of 75, and then x equals natural log of 75 minus 1 all over 2. Okay, in this example we have 2 natural log of x equals 4. So if we isolate the natural log of x, this equals 4 over 2. Then the natural log of x equals 2. Now what we can do is exponentiate, like we explained before. So we take e to the natural log of x equals natural log of 2. Now because e and the natural log cancel each other out, we get x. Sorry, that should be e to the 2. We get x equals e squared. Let's have an alternative. If we have natural log of x squared equals 4, then e to the natural log x squared equals e to the power 4. X squared equals e to the 4. So x equals square root of e to the power 4, and x equals e2. The natural log of 3x equals 5. Exponentiate, so we have, take e on both sides, so take e natural log of 3x equals e to the power 5. So therefore this e and this natural log cancel each other out, so we get 3x equals e to the power 5, x equals e to the power 5 over 3. Natural log of x plus natural log of x cubed equals 4. So what we can do is natural log of x plus x cubed equals 4. So the natural log of x to the 4 equals 4. Exponentiate now. So we have e to the natural log of x to the power 4 equals e to the 4. So this cancels this out, and we're left with x to the power 4 equals e to the 4. So therefore x equals e. Okay, in this last example, natural log of e to the natural log power natural log x minus natural log of x minus 5 equals the natural log of 2. First of all, we see that we have a natural log and an e next to each other, so they cancel each other out, so we're left with natural log of x minus natural log x minus 5 equals the natural log of 2. Here we use the properties of logs, so log laws. So this becomes the natural log of x goes on the top and then x minus 5 on the bottom equals the natural log of 2. Now we can cancel the logs, natural logs, because they're in the same ratio. So this then becomes x minus 5 equals 2. X equals 2x minus 10 minus x equals minus 10, and x therefore equals 10. If we were ever asked to draw the curve for the log of x, say it was f of x equals log base 2 of x, x equals 2 f of x. Quickly draw a table. So this would be x, this would be f of x. So for 1, we could say what power of 2 gives you 1, so it's 0. So for 2 it's 1, for 4, 2, for a half it's minus 1, and for a quarter minus 2. So if we quickly draw this, we get the curve will cross the x-axis at 1, and then it'll go down to half, it'll be minus 1, about there, and at a quarter it'll be minus 2, so around there, and then it'll go off at 10, like exponentially that way, so it'll go like that. So this is log 2 of x. This has a vertical asymptote. Has a domain of x is greater than 0, and the range is all real numbers. If we have a look at both graphs together, so we would have e of x going through 1 here, so it would go here and then go up, so this is e of x, and then to find the inverse we reflect in the y equals x axis, and that would give us a curve that would look like that, and this is actually the curve for log x. So log x and ex are the inverse of each other. E is usually used in equations involving exponential growth, so like say colonies or bacteria, things like that, or interest or compound interest on money. Let's have a look at a typical question. The mass m grams of a substance is increasing exponentially with this equation. Find the time for the mass to double 1. Find the time for it to reach 8 times its initial mass. And 3, find the rate of increase at mass equals 400. Right, so for what we have to do is find the initial mass. This is the first thing we need to do. So the initial mass is at time equals 0. So when t equals 0, the mass equals 250 e to the 0. So that means it equals 250. So the initial mass So we want to know the time taken for the mass to reach double its initial value, which is 250, so it's going to reach 500. So 500 equals 250 e to the 0.021t. So we divide the 500 by 250, we get 2 equals e 0.021t. Then we take natural logs on both sides, and here it would cancel the e out. So this would be natural log of 2 equals natural log of e 0.021t. So this would cancel, this would make the log. Natural log of 2 equals 0.021t. So t then equals 1 over 0.021 times the natural log of 2, so which is approximately 33.0 hours. So the question, we find the time taken for it to reach its 8 times its initial value. So what we have to remember is, what does this 33 represent? So this 33 represents the time taken for it to double its mass. So 33 is double, which is 2 times. So after another 33, which is 66, it's going to be 4 times. And then after another 33, it's going to be 99, is 8 times. So that's your answer. 99 hours. When it says rate of increase, we need to differentiate. So we have m equals 250 e to the 0.021t. So therefore dm by dt equals 200 sorry, 250. So dm by dt equals 250 times 0.021 e to the 0.021 t. So at 400 grams, we want to know what t is. So this works out as 5.25 e to the 0.21 t. So here we have 400, like we did in the initial question, equals 250 e to the 0.021 t. So 1.6 equals e to the 0.012 t. So the natural log of 1.6 equals 0.012 t. So t equals 22.38. So now we know the time taken for it to reach 400, and we know the rate of increase. We just put that t value into there, and we get 8.4 grams per hour.